We all agree that wild push may be a great way to getting started, but propulsion is the only way to keep going. Distinguished delegates, colleagues from automotive industry, eminent speakers, fellow ICATians, ladies and gentlemen, a very good morning to all of you. I, Asta Dwivedi, on the behalf of International Center for Automotive Technology, Aspire Management, let me extend a very warm welcome to all of you for this webinar on EVSE and battery pack design for EVs. International Center for Automotive Technology, ICAT, located in the Northern Automotive Hub of India, is a leading world-class testing, certification, and R&D service provider under the aegis of NATREP, Government of India. Aspire is a technology platform. ASPIRE stands for Automotive Solutions Portal for Industry, Research, and Education. Aspire has taken an initiative for conducting various webinars on topics which is a part of celebration of Azadi Ka Amrit Mahotsav, which is 75th anniversary of our independence, of aiming to reinforce the Atmanirbhar Bharat in technology area. It is our privilege to have you all with us today for this webinar. Through this webinar, we have set a virtual stage to connect in the industry, to indulge and to acquaint ourselves with emerging technologies on EVs and trends. Now, for today's webinar, we have following speakers. Dr. Santanu Mishra from Ministry of Skill Development and Entrepreneurship Chair Professor, IIT Kanpur. Dr. Engineer Yashodhan Pramod Gokhale, Vice President of Business Development from Octillion Power Systems India Private Limited. We will start with the presentation now, and if you have any questions during the presentation, just write them in the chat section and we will take that question on your behalf at the end of the session. I also request all the speakers to kindly keep their presentation ready. I'm sure that the immense knowledge in the session will help us all greatly. So, for the first presentation of the session, please join me to welcome Dr. Santanu Mishra from Ministry of Skill Development and Entrepreneurship Chair Professor, IIT Kanpur. He received a BTech degree in Electrical Engineering from the College of Engineering and Technology, Bhubaneswar, India in 1998. MTech degree in Energy Systems Engineering from IIT Chennai, India in 2000. And a PhD degree from the Department of Electrical and Computer Engineering, University of Florida, Gainesville, USA in 2006. He worked as a senior application engineer with the International Rectifier Corporation in Rhode Island, USA from 2004 to 2008. In 2017, he was a visiting chair professor at CPS Virginia Tech, USA. Currently, he is the Ministry of Skill Development and Entrepreneurship Chair Professor at IIT Kanpur, India. His research interests include power converter design, implementation, control, and application in rural scenarios. He has served as associate editor of several journals including IEEE Transaction on Industry Application, IEEE Transaction on Power Electronics, IEEE Consumer Electronics Magazine, IET Power Electronics, and IET Rapid Communication. Now, we welcome you also. Please take the session now. Thank you, sir.
Yeah, ma'am, are you able to view my screen now? I just want to check.
Yes, please. Yes, please.
So please start the session.
Okay, so are you able to view my screen?
Sure.
Yeah. Okay. Thank you very much for the nice introduction. I am Santanu Mishra. So I basically am from electrical engineering. So what we will do in today's session is that we will discuss about electric vehicle and charging infrastructure from a electrical engineering point of view. I will not go into tactics, markets, predictions, etc., because this is not what I have any knowledge about. So just to start, So, like the introduction said, I have been in this field for quite some time, and I serve as a consultant to many of the companies in India before I joined here. And then let's start our presentation for today. So this electric vehicle there is nothing new to this electric vehicle. This has been there for quite a while. Sorry. Okay. So this has been there for quite a while, and in 1966, General Motors came up with this with their first electric vehicle. They used to call it Electrovare. And then Enfield also had their own electric vehicle. But what has changed? Why people have all of a sudden become very passionate about electric vehicles? So the main point that I can see about it is the evolvement of battery technology, and it has become more affordable right now. But let's see what are the electrical aspects of it. So if we go to the next slide. So electric vehicle is nothing great. What it basically is instead of taking combustion fuel, we use battery to power our vehicle. So as we are using battery to power our vehicle, so it is kind of it kind of requires power electronics. So it requires more involvement of power electronics compared to a general combustion internal combustion engine. And what else it wants? It wants electricity to charge the battery rather than having fuel, combustion fuel, like fossil fuel. Right, so this is the basic architecture of an electric vehicle. So if we go to the next slide, so there are many types of electric vehicles that are there. So the most pure electric vehicle is the battery electric vehicle, because battery electric vehicle uses only the battery power to power itself. Other than that, plug-in electric vehicle as well as hybrid electric vehicles, they both will use the gasoline in some way or the other, petrol in some way or the other, petrol or diesel in some way or the other. So, so battery electric vehicle is the pure one. So mostly, I mean, currently, even though electric vehicles are very popular, still I will say that hybrid electric vehicles have a further reach into the market compared to battery electric vehicle, and that is precisely why we are now, all of us are working on to bring this battery electric vehicle to the system, to our society, right? So so if we go forward, so then this picture is generally giving you a overview of what is the difference between an internal combustion engine, plug-in electric vehicle and battery electric vehicle. So it is color coded, and you can basically see that in both plug-in electric vehicle as well as battery electric vehicle, there will be this yellow component, that is this yellow component here, that is the power electronics component. Okay, so that will be new in electric vehicle. Other than that, there will be a huge battery pack, so which will be helping us in the operation of the car. Right. Other than that, I mean, the rest of the things like motor, etc., are there. I mean, they're in both of them, and the torque coupler is there. So many things are common. Only the energized, how to energize this movement of a car is what is different here. Here the energization is mainly from battery, and in internal combustion engine the energization is through fossil fuel. Right. So so if we see some of the specs, these specs may be a little bit old, like a couple of years old, but I mean, it will give you an overview of how electric vehicle manufacturers provide us the information. That is precisely what I'm trying to show here. And what we will see one by one is how are these electrical information that is provided in this spec relevant to our presentation and relevant to our knowledge on electrical engineering. All right, so let's take the example of Nissan Leaf. So what they are saying is that Nissan Leaf in 2000, it's couple of 2-3 years back, they used to have a 30 kilowatt hour battery. Now it has increased, and the battery voltage is 360 volt, and the range is 107 miles. Onboard charger is 6.6 kilowatt, and miles added per charging is 23.54. Now the question is, how do they come up with this battery size? How do they come up with this battery voltage? How are they coming up with this range? And what is this onboard charger? And how are they calculating this miles per charging? So this is something that we will see, because this is the electrical point, right? So let's see. So when they are saying size of a battery, so that is actually basically they are telling you the range of the electric vehicle. That means if you have a bigger size of battery, naturally your range will be more. That means if you fully charge your battery, you will be able to go a longer distance. Okay, that is precisely what it means. All right. Now from there, you can actually deduce per hour of charging how much kilometer you will be adding. Like for example, for Nissan Leaf, if the range is divided by the battery size and multiplied by the charger, then you will get this 23.54. If we go back, you can see that this is the range 107, this is the battery, and this is the onboard charger. So what it is saying is that if I charge my battery for 1 hour, so if I charge my battery for 1 hour, how much energy I will be putting in the battery? It will be 6.6 kilowatt. So if I am putting 6.6 kilowatt, that will correspond to this much, this 23.54 miles per hour. The reason is that if my battery would have been 30 kilowatt hour, I can go 107 miles. So if I have 6.6 kilowatt, naturally I can go 1/5 of that. So that is what this number will mean. All right. So now second question is that miles added per hour of charging. So this will depend on two factors. This will depend on battery size as well as charger size. For example, let's say when I am saying miles added per hour, I am assuming here that I will be using the onboard charger, which is 6.6 kilowatt. Let's say I use a higher wattage charger, let's say 100 kilowatt charger, then miles added will be far higher, right? Because now in 1 hour, instead of giving 6.6 kilowatt, I can give 100 kilowatt. So that is precisely why miles added is dependent on not only on battery size, it is also dependent on the charger side. And when they talk about charging of a battery, when they specify this charging of a battery in electric vehicles, they actually generally mean from 20-30% to 80%. Okay, it is similar to our cell phone. So our cell phone also has a lithium ion battery, and you must have noticed that till 90% our cell phone will charge very fast, and after that it will charge slowly. The reason actually for that is from electrical point of view, that from 30 to 80% it is charging like a current source. So the charger is working like a current source and putting current into the battery. So as it is putting current, that is charge, into the battery directly, so therefore the charge is increasing very rapidly. But after 80%, the battery is incapable of taking that charge. If we still try to put charge into the battery, it will heat up. So therefore people do tickle charging. Tickle charging means it will do a very small current, you just slowly charge and somehow get to the 100% mark. So same principle that is used in our cell phone charger or laptop charger is also applicable to electric vehicles. All right. So then third one is rating of the battery. So you can see here that the battery rating was 360 volt. So now the question that I always had in my mind was, how did you come up with this 360 volt? Why 360 volt? Why not 180 volt? Why not 100 volt? So the reason for that is that first thing is that they actually put cells in series to create this higher voltage. Now the question is, why higher voltage? So the reason is this. So let's say we have a like a 100 kilowatt charger, fast charger. Then my battery voltage is 360 volt. So what that means is that 100 kilowatt divided by 360 will be the current that I will be putting into my battery. So my battery current will be 277 amps, which will be pretty high. So you can imagine that if the battery voltage would have been 48, then the charging current would have been 100 kilowatt divided by 48. So that the current will be huge. So this huge amount of current is what we kind of avoid in electrical engineering. The reason is that if your current is very high, then it will create a lot of loss in the wires. So this concept is very similar to what we do in power system. The power system, our generating station, let's say in Rihand or any thermal power station, the voltage at which the generator works is about 13 kV. But then we will step it up to 100 kV, 200 kV or 220 kV or 440 kV and then transmit the power. The reason we go up in voltage is because we want to reduce that current. Because if we reduce the current for the same amount of power, then the wire loss will be kind of reduced. So this heavy current is something that we are trying to avoid. That is why we use a very high voltage battery. And when you say that a heavy current needs to be provided, we actually mean that bigger wires need to be provided to charge this battery, right? So this bigger wire means more weight in the car. So that is something that we are trying to avoid, right? So then let's talk about the charger. Before I go to the charger, if there any question, I can just take it up quickly. Okay, should I go ahead? Okay. Okay, am I audible? It's all right.
You are audible, sir.
Okay, all right. Okay, so just wanted to make sure. All right. So please let me know your question whenever it is there, or put it in the chat box, and I will take care of it at the end. Okay, so let's talk about the charger. So there are two types of chargers that are there, as you know. One is a onboard charger, another is a DC fast charger. The reason there are two types of charger is that when it is something like when we buy a cell phone, the company provides us with a charger, right? So so it is something like that. This onboard charger is something like that. When we are buying a car, the car comes with a charger of its own, but the charger is fitted into the car. Now you can imagine that when the charger is fitted into the car, the weight of that charger actually matters. Okay, so if I put a 100 kilowatt charger, that will be bulky and that will have a lot of weight. And when we are talking about electric vehicles, we are operating the vehicle with battery power. So therefore, we don't want to carry a lot of dead weight. All right, so what we call a dead weight, right? So therefore, a onboard charger is generally provided with the battery. Like we saw in Nissan Leaf's case, it is about 6.6 kilowatt, which will be placed in the car itself. So as it is placed in the car, the rating is a little bit small, but the charger is capable of working from our AC supply that is there in our home. All right. So therefore, obviously, if it is there in our home, naturally the power cannot be very high. Our home only has a certain amount of power handling capability as far as the grid is concerned. But if you use a DC fast charger, the power electronics part is placed outside the car. So if the power electronic part is placed outside the car, you can see that it can be of any size. There is no problem. But then the question is that if the power electronics part can be placed outside the car, why are we not generating, let's say, one megawatt or a 100 megawatt charger, and that will charge my car in a flash, right? So that is one of the questions I always had, and I asked my friend in Nissan, why aren't you using a 100 megawatt charger? Okay, 100 kilowatt is available. Use a 100 megawatt. It will in a minute you can charge your battery. The problem there is that whenever the car comes, it has a certain infrastructure that is already placed inside the car. So normally, in order to reduce the weight, etc., with the present technology, what they have done is that they put a particular type of wire inside this car, which will take the current, right? So this wire is actually limiting how big a fast charger you can have outside. All right. I can always say that I can have 100 megawatt, but that will lead to a huge amount of current here. 1000 amp of current here in this wire, and that wire may not be capable of taking that current. So that is the limiting factor for this fast charger. So whenever a car company will tell you that you can use a fast charger, they will generally give you what is the maximum rating you can have for that fast charger. So that is the limitation point. So like we said, there is a AC charger which is on board. That is like our normal cell phone comes with a charger, so our car also comes with a charger. Then the second part is that we can actually charge from outside, which is called fast charging. All right. So let's go to the next point. So the next point is kilometer added per charging. So obviously the fast charger is a little bit smaller, like I said, because it is placed inside the car. So as it is a little bit smaller, so naturally the kilometer added per hour will be a little bit smaller. It will be not little bit, it will be far smaller. Like it will be generally for overnight charging. So you can just put the plug in the vehicle and forget about it, and your vehicle will charge. All right. But then there is a DC fast charger. So this DC fast charger, like I said, is directly charging your battery. It is not going through any power electronics. So all the power electronics are outside the car. So only thing that is coming out is the battery voltage. This plug will provide and directly charge your battery. So therefore, this kind of charging is much faster, and it will provide you a much higher kilometer per hour of charging. Again, I will just reiterate that this DC fast charger cannot be of any rating because it is limited by the wires that are used inside the car. All right. So let's go to the next point. So just to make things simpler for us, what this DC fast charging, there are certain guidelines that are provided. Okay. So these guidelines, like for example, this CHAdeMO is one DC fast charging guideline provided by Japanese manufacturers. So they have a plan that by 2016 they will go up to 50 kilowatt, 2018 150 kilowatt, 220 they will go higher rating. So when they are saying that, all they are saying is that by 2018 whatever car we will sell, it will have the wires such that it will take higher power. That's all they are saying. Okay, by 2016 whatever car you buy, it can only take 62.5 kilowatt. That means the wire that is there inside the car is only limited to 125 amps. Then when in 2018 we will increase the wire size so that it is 350 amps, etc. All right, so that is the roadmap they will have, and based on that they will work. All right, so I'm just trying to tell you from an electrical perspective, how do you read these plans and this technology that is there around us? All right. So let's go to the next slide. So now the question is, when do we use 3-phase and when do we use single phase? Because you must be aware that in our house we have single phase. All right. So every equipment is single phase, but some people can have 3-phase connection. There is no problem. You can actually request the company and they will provide you a 3-phase connection. But the question is that when do you go for a single phase and when do you go for a 3-phase? So if you look from an electrical point of view, just look around your house. If you have single phase, the maximum plug point you have is 15 amp plug point. So if you have a 230 volt and 15 amp plug point, the maximum load you can put in that 15 amp plug point is 3.5 kilowatt. So above 3.55 kilowatt, if you want to go, your relay will trip. Okay, your MCB will trip. So this is what limits the single phase. And this is assuming that you have unity power factor. So if you do not have unity power factor, then this 3.5 is no longer 3.5. It can go down to 3 or something like that. All right. So this is limiting how much power we can get out of our plug. So if this is the power you can get out of our plug, then obviously this is telling you what is the maximum power I can support when I connect my electric vehicle to it. Okay, so if I put my onboard charger of my electric vehicle, if it's a 6.6 kilowatt charger, obviously it cannot be connected to single phase. It has to be connected to a 3-phase. All right, so if you are buying a Nissan Leaf which has a 6.6 kilowatt, then what you have to do is that you have to actually ask the electricity company to give you a 3-phase, and then only you can charge your car, right? So, and obviously you cannot put a 100 kilowatt charger in your house, because the maximum power you can grab is 3 kilowatt or so. All right, so this is kind of limiting you that when to use a single phase and when to use a 3-phase. So invariably you will see that all the DC fast chargers are in 50s or hundreds of kilowatt. So they will be outside somewhere, and they will be supplied with a dedicated 3-phase power supply to itself. All right, so that is what is the distinguishing feature of a DC fast charger. All right. So now let's talk about an electric vehicle from a power grid perspective. All right. So from a power grid perspective, it is very easy to say that I will put a 100 kilowatt charger there, I will put a 50 kilowatt charger there. But what is its impact to the electric grid? So from the electric grid point of view, if you are having a 100 kilowatt charger and charging only one car, all right, so your input current is 100 kilowatt. Input power is 100 kilowatt, and your input current is 131 amps. That is assuming unity power factor, because it's a 3-phase. That's why this formula is used. It is 100 kilowatt divided by √3 into 440 volt. 440 is the line to line. So line current will be 131 amps. So that is kind of huge, because it is only one car. Let's say there are 100 cars, then this will be 100 times of this, which is a huge burden for the electric power grid. You can think that let's say there are 100 cars put in our distribution grid at one time, then 100 kilowatt times 100 will be the demand of the fast charger. Maybe a little bit less than that, but you can see the magnitude of power demanded from our power grid. And some of the solutions that people are proposing for it is that they are saying that, okay, we will ask people to charge at night, this and that. So these are all I will say not practical solution, because once the car is sold to a person or a family, I don't think government has any control over how or when they will charge a car. They will charge a car as they need it. So the solution has to be more user independent. All right. Even though I will concede to this point that from a planning point of view, having a time of charging has an impact from a timing from a planning point of view, but I don't think from an application point of view it has any impact, because we will charge whenever we want, right? So the solution that is generally that we generally work on in academia is so that we will actually put some support to the fast charger. So in other words, what we mean is that, let's say 100 kilowatt is suddenly demanded by a car, then that 100 kilowatt will actually come from a battery. Okay, suddenly, okay, it will come from a battery. Okay, and then the battery will discharge. So let the battery discharge and let the car get its charge and go away, and slowly from the 3-phase we will charge the battery back. Okay, because the battery can take hours to charge. It is a static battery. It is placed near the fast charger itself, right? So that is why we can get away with. So this is one of the solutions that people generally work on. So if you see a very fast charger, you will see that there will always be some kind of external power support. So it can be a battery, it can be a solar energy. Some kind of external support will be there. The reason is that if you have that external support, then the sudden power demand from the 3-phase will be kind of less. Okay, so that is the whole idea here. All right. So let's talk about power electronics part of it. So I'll just quickly go through the power electronics part. So as I pointed out, that there are two types of chargers. One is a onboard charger, and second one is a DC fast charger. So the onboard charger, like I said, is taking a three-phase, taking a AC supply. It can be three-phase or single-phase, and giving out a voltage that is compatible with the battery. So let's say the battery voltage of the car is 360 volt. The onboard charger will also give you 360 volt. It will take 230 volt single phase or 440 volt three phase and give you a 360 volt single phase, 360 volt DC voltage. So that will be provided by the onboard charger. The DC fast charger will exactly do the same thing. It will take a three-phase supply and give you a 360 volt. So the output of the charger has to be connected to the battery. So the output of the charger has to be in line with the battery voltage. So if the battery voltage is 360, so the DC fast charger or the onboard charger, the output has to be 360, nothing else. All right. So now, if we look from power electronic perspective, it is actually this kind of circuit is actually used. They call it a rectifier. So there are four types of power electronic circuit that are used in practice. One is a DC to DC converter, which is there in battery powered system. So internally, let's say we have to turn on our entertainment system inside the car. So it is taking power from the battery. So there is one DC, and then there is a LED backlight for the entertainment system. So that is another DC. So that will be converted by a DC to DC converter. So similarly, there will be a DC to AC converter. This is like our home inverter. We have a 12 volt battery and we get 230 out of it. And this is a rectifier. So this is rectifier is something like a AC input and a DC output. So this DC to AC inverter, like some manufacturers are working on grid to vehicle to grid technology. That means when power is not there, instead of using an inverter, you can use your car to power your home. Okay, so that will use this DC to AC inverter, because this DC will then be the voltage of the of your car, which is 360 volt, and we are getting a 230 volt out of it. So that is something that have been used. But mostly the present day cars are not equipped with this technology, so they can kind of use this kind of onboard chargers or rectifiers. So only difference will be the size of these power electronic component. And if you look from an engineering power electronic perspective, a converter has many parts, and one of the major part that is taught to us in our power electronic courses of undergraduate is this power stage, but it also has this control stage, which is not covered that well. But actually this control stage is one of the most important part of a converter. So in other words, what we are saying is that if you are trying to have a rectifier which is taking a 230 volt and generating a 360 volt DC, then this V input is a AC and this load is a DC. So now this controller takes care whether this power stage will work like a current source or a voltage source, because when your battery is not fully charged, this power converter will work like a current source, because now I want to charge my battery faster, so therefore this power stage will work like a current source. And when the voltage of the battery kind of goes up and reaches to around 360 volt, then this power stage will work like a voltage source for the battery. So this power stage is basically the source, either a voltage or a current source for the battery. So this is achieved by this control stage. And a power electronic converter, I mean, these stages are not very distinctly defined. This is one of the converters that we have designed in our lab. You can see that it is a very compact structure. Everything is inside it. But I mean, there is this classification as far as block diagram is concerned. So if we look at the efficiency, this is one of the most misunderstood component of power electronics. So this is efficiency is generally we call it a managerial term. Managers used efficiency to sell products. Okay, but designers like me will not use efficiency a lot. The reason is this. The reason is that actually the efficiency of a converter varies with load. Okay, so at lighter load, the efficiency of any converter will be low, and at somewhere in the middle, it will kind of reach a peak, and then it will go down. It is possible that this peak efficiency is at 100% load. That is possible. There is no problem. Okay, so there are designs available where this peak efficiency is kind of designed in such a way that it is at 100% output. But whenever the point I was trying to make here is that whenever we talk about efficiency, it is not a single number. It is actually a multiple number. But what we specify when we specify efficiency is the peak efficiency. All right, because that is the best that we can get out of it. Now the question is that why is there efficiency? If we are giving, let's say it is a 100 kilowatt charger, and I am giving a 3-phase supply, and I am getting some DC out of it for my battery. So if I am giving 100 kilowatt, I should get 100 kilowatt. But that is not the case. If you want 100 kilowatt at the output, you may have to give 110 kilowatt or so, a little bit higher than that. Okay, the reason is that these converters that we saw, have losses. Okay, and there are mainly two types of losses. One is conduction loss, and another is switching loss. These are dependent on the types of switches and type of topology that you are using. All right, and generally the efficiency will be very good, but it is not always true that it will be good. Okay, there is a reason behind it, and I will cover that in the next few slides. So I just wanted to summarize here that efficiency is not a single term. With the output power, the efficiency will kind of vary. So whenever efficiency is specified, one number is specified, they are generally talking about the highest efficiency that you can get. All right, so now one of the major misunderstood concept about efficiency as far as power electronics is concerned, this is absolutely misunderstood, I will tell you, is that everyone thinks that a converter should have 100% efficiency. Okay, that is, yes, it is desirable to have 100% efficiency, or it is desirable to have a converter which has very high efficiency, but it is actually not true in practice. Why it is not true is, let's say for example, we are powering a cell phone. A cell phone is a 10 watt charger, so very small wattage requirement is required. So if you are a 10 watt charger, you have 99% efficiency, the converter will become very complex. In fact, we want to make the converter that is inside the cell phone or the charger that is powering the cell phone very simple, so that it can be used anywhere, it can be repaired anywhere. And in doing so, actually we will incur a little bit of loss, which is okay. The charger that the cell phone charger or the laptop charger will have a 90-95% efficiency. The reason is that I mean, even 10% loss is fine. Okay, so because as long as the cost is low. All right, but if you are working on a 100 kilowatt converter, let me just point this out in the next slide. So let's say Rihan, Dadri Rihan, there is a HVDC line. It has a 1500 megawatt converter there, right, which is for 500 volt. So if this converter has 99% efficiency and it is processing 1500 megawatt, then what will be the loss? The loss will be 15.15 megawatt, which is extremely high, because all this loss is becoming heat, and 15 megawatt of power loss will generate a huge amount of heat. It has to be removed, otherwise it will burn the switches. So therefore, a very high power converter having a 99% efficiency is no good. It should have 99.99% efficiency, because then the loss will be a little bit smaller and it will be more reasonable. to operate this system. So therefore, you will see that if I go back to the slide, as we go up in power rating, our efficiency number will actually improve. The reason is that it is not improving by choice, it is improving by design. We cannot incur a little very high loss when we go up in power rating. So generally that is why it is very misunderstood. People will see a 100 megawatt converter which has a 99% efficiency, and then they will expect that a 1 kilowatt converter should also have a 99% efficiency. That is, yes, desirable, but it is not economically viable, because in a smaller converter to achieve the very reason we have a smaller converter means we are actually going up in switching frequency and reducing, miniaturizing the devices. So by miniaturizing the devices, we are actually incurring some loss there. So therefore, it is not advisable to have a very, very high efficiency at very low power. Let me just go forward. I don't have a lot of more slides. So these are the switching technology that are used in practice. Normally, silicon MOSFETs are used up till 100 kilohertz and 10 kilowatt rating. But above that, if you see a 100 kilowatt rating converter or a DC fast charger, they mostly will be using a IGBT based device. Slowly, silicon carbide is coming up. It is very expensive right now. That is why IGBT is still used in practice. But mostly it is, I mean, it will be slowly replaced by the silicon carbide MOSFETs as well as IGBTs. So this is a silicon IGBT. This is a silicon carbide MOSFET as well as IGBTs are there. So that will be used in future. But these GaN devices, even though people say that they have very good performance, but they have mostly been in the low power rating scenario, below 1 kilowatt type of a thing. So what we have seen is that below 1 kilowatt, these GaN devices actually work very well, because after that because see, the very purpose of using GaN device is to have a very high switching frequency of the converter, and the reason of having a very high switching frequency is to miniaturize a converter. Because when you go up in frequency of a converter, switching frequency of a converter, you are actually miniaturizing it, making it smaller and making it more lighter. So that is not very much required when we are making a DC fast charger. You don't have to make a DC fast charger lighter. It will be placed in some place and it will be just there, sitting there, right? So that is why it is okay to use something like a IGBT or something, as long as the efficiency can be increased to a very higher level. So there the efficiency is very, very important. All right. Here the miniaturization is more important. Efficiency is not that important because the wattage rating is kind of small. So let's go to the next slide. So as far as magnetics are concerned, what we have is in power system we use iron core, which is called CRGO core. And as we go to power electronics, we tend to use ferrite cores. The reason behind that is that as we like when we in power electronics we use higher switching frequency, so their eddy current loss will be very high. So this resistivity is the one that defines what we use in power electronics. So if you take ferrite core, it has a much higher resistivity. What that means is that this core is also a metal. So if you have a signal that is having high frequency, that will kind of inject some current, that will induce some current in that core. So that current has to be small. Then the loss in this core will be small and it will be kind of cool. It will not be hot. So that is why what we do is that when we go up in switching frequency in power electronic converter, we tend to use ferrite kind of cores. All right. So if you use ferrite kind of cores, you can just see a comparison. This is a comparison of a 5 kVA transformer, which is power transformer, and a 5 kVA 20 kilohertz transformer. The size reduction is huge, all right, because we are using, it's much lighter and the size is reduced. So this is a for GaN application, what we use a 100 kilohertz converter here, the same converter, same converter uses a transformer which is 1 megahertz, and you can see the size of the reduction in size of the transformer is used, and that is what makes it mobile, right? So in mobile application we go up in switching frequency, and definitely this converter will have more loss than this, because it is more miniaturized. So naturally physics will dictate that that whenever there is a loss, there is heat, and this being a bigger surface area, the heat dissipation will be faster. This will be a little bit slower. So that's why efficiency can be a little bit smaller, but miniaturization is what we are looking for. Right. So let's go to the last part of the slide, which is what we are working on here at IIT Kanpur. Like I told you that there is always a battery support when we charge. So we didn't like that idea, and we about 3 years back we proposed that we should have solar backup for that, and we got some money from Mission Innovation from Government of India, and they provided us to work on chargers. So I kind of specifically wanted chargers for our e-rickshaws, because that is what was very prevalent in places like Kanpur. Okay, there is no electric vehicle here. Okay, even though we talk about it, it is very hard for us to get an electric vehicle here in Kanpur. We have chargers, but we don't have electric vehicles. All right, because that is kind of hard. But electric rickshaws are everywhere. So that is why I wanted to work on a self-developed technology on how to charge a e-rickshaw, and this technology actually is ready, because the project is towards its end, and we have demonstrated this whole concept properly. So I will just give you an overview of that. You can see that these are the converters that we have built. It looks a little bit bigger, but it's not that big. It is actually within this rack. Everything comes, and it can charge about 2 to 4 e-rickshaws in parallelly, no problem. And the beauty of this technology that we have developed is the power management scheme. So we have a central controller that is inside this, which is managing all the power. So what it does is that it will try to take most of the power from the PV panel when it is available, and the least amount of power from the grid. All right, and charge your electric rickshaw. But let's say at night it will take only the grid, but at daytime it will try to take maximum amount of power through the PV panel and less amount of power from the grid. The challenge there is that in a sunny day you can have clouds on top of this PV panel. So let's say this panel is giving out all the energy, all of a sudden cloud comes. So when cloud comes, this power management scheme will make sure that nothing stops. It will just transfer all the power to the grid and relieve this PV panel from all whatever PV panel can give, it just take. But as soon as the PV panel is back again, it will reduce the grid power and increase the PV panel power. So that is the power management scheme that is integrated into this system. So that is one of our major. So apart from all the converters that we have designed with a company, we have also designed this intelligent central controller that is taking care of this power management scheme. So these are some of the data that is provided, like from PV to grid to battery, when both of them are there, how the system is performing. Then when only PV is connected, how the system is performing, and when the grid is connected, how the system is performing. So all these things are tested. We are designing a pilot which will be kind of installed in the couple of months. This COVID has hit us a little bit because all our students have been asked to go home. So as soon as they are back, it will be back in running to just install this pilot, because all the designs, all the modules, the pilot converters, etc., are there in the lab. It is just that it has to be installed. All right, so that we will do in the next couple of months before the end of the project. So these are some of the converters that we have designed. Smaller power converter, apart from, I just showed you a bigger converter which is for e-rickshaw, but there are many other technologies that we develop in the peripheral system, that is a GAN system, one small converter we have made, and then we have made a power amplifier. These are all technology developed by our students who have gone on to work in various companies. Like Shubham is working for GE, Vansis and Kapil, they were both working in Bangalore for some IC design company. Sonam is a PhD student of mine, and Hemant is working for Intel. So they're all students who have developed this technology, and they are with us. Right. So that will kind of conclude my presentation. If you have any questions, I can take it up. Is there any questions? I didn't see any question on the chat box, but if you have.
Thank you, sir. Thank you for your immense knowledge, and it will help us all greatly. We have few questions from our audience. Solar connected system. This question is from Vinay, Mr. Vinay. This question is that solar connected system is interesting, and when no charging load is there, then solar panel power is used to charge stationary batteries or not?
No, okay, Vinay, it's actually a very nice question you asked. In our system, we didn't have any battery. We actually avoided battery. So the problem with batteries, even though it is talked about a lot, and from a practical perspective, actually the battery has a life, which is what actually switches us off. So what we instead did was that whenever solar panel is there and no vehicle is there, we are actually feeding the power back to the grid. Okay, so that way we are actually contributing to the grid power as well. So that is the strategy we took. Does that answer your question?
So another question: can we link phase changing material with the solar for power storage? From
phase changing material. Okay, so see, this is precisely what I told you in the beginning of this lecture, right? I will not go into tactics, market, and prediction. I am only concerned about electrical engineering aspect of it. The reason I will not go through it is because, I mean, just give an overview of where I am coming from. So in my last 12 years in this field, and probably 10 years in the industry, what I have seen is there are many technologies which are great, but they never took off. But there are many technologies which were not that great, but they took off. But so what drives a technology and what doesn't drive a technology is very much dependent on many other aspects like market, funding, where the funding is coming from, whether profit is there or not. So that is not something I'm good at. So I will only be discussing about the technical aspect. And your question doesn't. I mean, it's not. I don't know the answer to the question. I will not say that it is not a good question. It is actually a very good question. I am not the right person to answer that question, whether phase changing material should be there or not.
So we have another question from Mr. Kudala Rajesh. He's asking that why communication protocol between Cadmo charger and vehicle?
Oh, the communication protocol, yeah, is there in my paper. I forget, I have a bad memory. There is a communication protocol that are there that they define. In fact, all the manufacturers will define a communication protocol. There is I wrote a paper on electric vehicle charging about 3-4 years back. There I have mentioned those. I can send you that paper if you like. Okay, I just don't remember the names of those communication protocols. But yeah, there is
Okay,
a
sir.
communication protocol.
We have another question from Mr. Raghavendran. The formula to calculate the miles from range, battery size, and charger power, does it need charging time to be included? The dimension doesn't match, like range, battery, kilowatt hour into charger kilowatt hour is equal to how many kilometer per hour?
Yeah, that's per hour, right? So that is where the time is included. So we are saying that if you charge for 1 hour, how much miles you are adding? So time is already included in that. 1 hour per 1 hour.
Another question from Mr. Mohit Kumar. Cars are high speed, low torque vehicles, while off road vehicles are low speed, high torque vehicles, like truck or tractors. How to decide best optimized battery pack and motor curve for best characteristic curve and optimum backup for off-road road vehicles?
I don't know the answer to this question, and even though I give an answer, that will not be correct. Even though anyone gives an answer, that will not be correct. Why? I will tell you why. The reason is that whenever a manufacturer gives you a car, okay, they do all this in the background and they give you a car. They will never allow you to touch the car. Okay, I'm telling you that you ask a manufacturer, let's say you design a very nice onboard charger and you go to Tata Motors and say that I will give you this onboard charger. They will not take it from you. All right. The reason is that whenever they are making it, actually they do a lot of background exercise of how that onboard charger is integrated into their car, because this car is their system now. Okay. So what motor they use, what kind of a car they use, what technology they use, that is all dependent on Tata Motors or where they're buying the technology, whoever they're buying it from, or they might be developing themselves. So if the question is that what kind of a motor should I use and all, I don't think you should be concerned about that unless you are working for a company. What you should be concerned about is what can you do outside the car, because that is something you can control. Okay, so it is something like that. There is a car, there is a charger. Charger is outside, it is in my control. Okay, I can design any charger. Car, I cannot touch the car. Actually, I cannot actually touch the car. I can say 100 things that I will make this motor, I can make this drive. All these things are all theoretical stuff. Unless you are working for a car manufacturer, no one will allow you to touch the car. All right. So only thing outside you can do. All right. So that's why I am more concerned about what is outside, that is charger. All right. I'm sorry I gave you a negative answer, but I thought that you should know what the realities are.
Yeah, but you are absolutely right, Professor Mishra. Like OEM, you touch the car, warranty gone. So you can't touch the car. What is inside and all that.
Dr. Gokhale, we just talked to one of the manufacturers. We bought a charger, EV charger. We asked the manufacturer that we want to enable your car for EV to grid. Okay, from the charger the EV will charge. There is no problem.
Yeah.
We said that can we work with us to make it EV to grid? They said that you cannot touch whatever we have given.
Yeah.
Just use it as is.
Yeah.
So we have another question from Mr. Mohit Kumar. What are the cooling options low cost available which are also waterproof?
Cooling options that are waterproof. Okay, currently they use mostly, I think, oil type cooling. So generally we will prefer air cooling. All right, because that nothing needs to be done, air cooling. But sometimes they can use oil cooling. In many of the cases they use oil cooling. In fact, in Tesla they use a little bit of oil cooling, if I'm not wrong. But that's about all I know about cooling. All right. So other than that, I mean, these technologies are evolving. Car manufacturers generally don't give us much information. My knowledge is purely based on what is available in the market. So oil, water cooling are there, but water they don't use. They generally use oil type of cooling or air cooling, like put a fan there or something like that.
Okay. Another question from Mr. B. Balaji from Chennai. What are the challenges involved in charging infrastructure?
Okay, so that's actually a very good question. Why is that people talk about fast charger and people talk about huge fast chargers. What are the challenges involved? The challenges involved are from a operational point of view. The challenges involved are how good your design is, how reliable your design is. Because see, if you are putting a charger somewhere, let's say in the Himalayas, okay, and if the charger goes bad, okay, then there is a 1 month downtime, because the charger has to be brought back, or someone has to go to let's say Uttarakhand, I mean to Srinagar in Uttarakhand and do it there. So this makes it very, very challenging for all of us. It's like using a vehicle, right? I still have a Honda Activa. Okay, that Honda Activa gives me the worst fuel mileage. Don't listen to what they are saying. It 45 kilometer, never. I'm telling you, it never gave me 45 kilometer, about 20 kilometer, 25. But it is one of the things that I rely the most, because it will never go bad. Whenever I turn it on, it turns on, and I can go and buy my mangoes or eggs or whatever. All right. So reliability is a far more important aspect as far as a consumer is concerned. You think about yourself. You want to buy a cell phone that works for a year. Okay, after that you will change, but you don't want that to go bad every 15 days and on the name of high efficiency, or greatness in how great the movie comes, or no, I mean you still want a reliable system, right? So that is one of the major challenges from the consumer point of view. But from design point of view, what are the challenges? That what kind of a technology of switch you are using, what kind of a technology of converter structure you are using, because all this will affect ultimately to the reliability of the system. All right, so switch technology, converter technology, cooling technology, all these things will affect the reliability of it. So there are two aspects to it, one from a consumer perspective, another from a technology perspective, and this is my answer to the question.
Okay, sir. So the next question from Mr. Srikant. What could be the op switching topology for onboard chargers as given in Indian grid conditions?
It's basically a rectifier. Actually, it's nothing great. It's a single phase to DC rectifier that they will use. Normally, they will use a bridge structure. They call it a PWM rectifier. Okay, high frequency PWM rectifier. That is something that they generally use. They can also use a unity power factor rectifier. Unity power factor rectifier has a diode bridge and a boost converter that will kind of charge. So these are the two technologies that is generally used for single phase. Okay, and if you go to three phase, then they use the purely PWM rectifier. There will be like an inverter, like a home inverter. Home inverter has two legs. This will have three legs in that, and that's about it. So home inverter converts a battery voltage to a AC. Okay. So here the idea will be to convert this AC to the battery. So which is also the home inverter is doing. It is charging your battery, right, from the local grid. So the same thing that they will use. The only thing is that it has to be made compact.
Okay, thank you, sir. Thank you for your knowledgeable session. It will help us all greatly. Due to time constraint, we have to quit the question answer session. Now, for the second presentation of the session, please join me to welcome Dr. Engineer Pramod Gokhale, Vice President of Business Development from Octillion Power Systems India Private Limited. Some of the projects he has been associated with as liquid cooled lithium ion battery packs and BMS deployment in India for electric cars and buses. Fuel cell bus project at Tata Motors Research Center, scaled up and optimized the process for high capacity lithium ion battery materials for the European automotive players and worked on lithium air sodium ion battery at Fraunhofer Research Journal. He has been awarded with Impact Champion Award, EPSRC Research Associate for Silica Nano Process, University of Strathclyde, Glasgow. Brian Scarlett Award for Outstanding Contribution by Royal Society of Chemistry for Titanium Dioxide and Silver Nano Particles Research. DFG and Marie Curie Action Scholarship for Innovation Research. Now, I welcome you, sir, to please take the session.
Yeah. Please, you can see my screen?
Yes, sir.
Yeah.
You
Okay.
can start the session.
Okay. Thank you. Yeah. Just a minute. Yeah. Thanks, ICAT, for giving the opportunity for this forum. Thanks for the team of the ICAT, Deve, Shudeep, Dr. Madhusudan Sochi, and other people, and SAE India. It's a wonderful talk, sir, Dr. Mishra, about charging and giving the understanding to everyone. So after the chargers, I'm just going to deep into a bit with the lithium ion batteries, how we make the packs and the new trends that which are coming up in near future. So these three young guys, Professor Goodenough, age 97, Stanley Whittingham, above 70, and Akira Yoshino, done excellent work in 1980s. For that, in 2019, they got Nobel Prize for developing lithium-ion batteries, their concept, fundamentals, and so on. So this was the case earlier. I just given the earlier shot where two cars are standing in the garage and one wanted to go. I'm from Pune, so I can say from Pune to Bangalore and Bangalore back to Pune in a single charge. At this stage, with the given situation, it is possible, but you have to put more battery pack efficiency and so on. And you can see on the right hand side, I'm going to talk a little bit about the chemistry, smaller amount of mechanical thing and electronic thing, how the packaging works and how it works. So whole the new development of the chemistry works with the three parts, mainly the cathode, anode, and electrolyte. So people are playing with the different types of structures, which is layered, spinel, or lithium rich. And then the anode, they are playing with the carbon, then the graphite, then silicon, then lithium titanate, and so on. And the more concentration on the lithium salt with the different additives to get the more transport phenomenon in electrolyte. So this is just to give you an overview how the development evolved during the course of time, where you can see in 1990, Sony come up with lithium cobalt oxide as a battery. There is an energy density, and as the time progresses, you can see the lithium iron phosphate with A123, which is commercially used in everywhere from laptops to various heavy vehicles. These type of batteries are used. People are trying to work on the sodium ion battery for the stationary storage, and lithium sulfur and lithium air battery, and so on. Professor Mishra has already mentioned many of the things. I'm not going to more details. Just to give you an overview, in this graph, it is plotted with power density. What is power? Is the how fast you can energy can deliver. The classic example of the power electronics unit that we use is the mobile phone. Now with the technology, we can deliver the, we can charge a mobile phone faster. because of the high power batteries which are used in the mobile phones. And this can be used with the combination of the batteries or capacitors. Then energy, how the capacity to do the work. So in a single charge, I can go with 500 kilometers or not. It can be defined by the high energy materials which implement to form the battery and which can deliver your demand. So people want high power so that you can charge your vehicle or indirectly they charge your battery in 15-20 minutes and go with 500 kilometers. That's the need people wanted. And we can see how people can achieve that in a which way. So this is a simple structure just to get the idea. Inside the lithium ion battery consists of cathode, anode, separator, electrolyte. Then CAN terminals. Then the cathode, there is a process for the battery pack making. Evolves the various steps. Mainly it is with the lithium rich materials can people use. Then the anode side, graphite use or the carbon based derivatives. Then the separator. Then electrolyte is filled in the system and so on. So this is just to give you an overview which involves the cell processing. I'm not going into details, just to give you, there is a different steps involve paste formulation, then the anode materials, cathode materials. So anode material consists of graphite, lithium titanate, silicon. Then people use different binders. Then these are the cathode materials you use. So this is to find the electrodes, anode and cathode. Then do the different measurement techniques for electrochemical methods, for the cell assembly, charge, discharge, impedance, and so on. Then do the electrocatalysis analysis, and so on. So far there are various types of batteries involved here with the different chemistries. Yeah. So mainly the lithium ion NCA chemistry commonly used in Tesla now, having the highest energy density, then have a power density, cell voltage between 4.2 to 3 volt, having larger cycle life over the calendar period, and so on. And this NCA chemistry can be in 18650, 21700. It's a form factor with cylindrical cells. Then you can have NMC, the another commonly used chemistry nowadays because of the high energy density, mainly used in electrical vehicles as well as for storage. Lithium iron phosphate is commonly used because of the safety, but it has lower energy density, having longer cycle life, can be used in prismatic and other form factors also. And then lithium titanate, which has high power material basically. So if you can see over the period, as in the previous lecture, it is very nicely mentioned, we can see the ICE engine with a conventional gasoline or diesel engine. And we can see at the bottom there is 0 kilometer. Then the size of the battery, the sizing of the battery plays a very important role. So if you wanted to go, say, for the higher range, there is a different starts, say from the micro hybrid, mild hybrid, then hybrid electric vehicles, and now it will come through the complete electric vehicles where the battery is the single source of the energy. You can reach from 150 to 500 kilometer in single charge with the combination from 20 to 100 kilowatt hour battery pack. Depends on the dimensions or the space available in your vehicle. You can put your battery pack and run with the desired kilometers. And as I mentioned, there are different types of the form factor of the batteries. This is one on the extreme left is the cylindrical cells, commonly called 18650 or 21700, depends on the diameter, like 18 by 650 mm size. Then in the middle, these are the prismatic cells, which can commonly use in Nissan and many other car industries. This is then pouch cell, which is also commonly used by Nissan and other companies. Different cell players manufacture different form factor, depends on their demand. So this cylindrical cell you can see at the here it's configured by anode separator cathode, and this is the arrangement where in the prismatic cell there are positive terminals, top plate, pressure vent, and so on. The same structure in the pouch cell also. When we design any battery pack, there are different types. Like first is design to value, and then design to cost. So one of the major objective is how you can design the safety and comfort, ensuring the various tests when you design the battery pack with the crash safety, vibration, thermal runaway, because thermal runaway is the crucial, then cooling efficiency, then the different types of cell types which are available, which can have the high quality, high performance, robustness. And obviously it can design to the costs. So how you can do with the high speed manufacturing with automatic or semi-automatic or robotic, whatever way, which can be a cost effective per unit. Over the sustainable and reproducibility plays a very important role. And then weight to size reduction. Then there are various methods for reduction, reducing number of part, optimize the material selection, choice of joining the technology, how you join the cells into modules and module to pack, and quality assurance and so on. So how you do the battery cells to module and module to pack assembly. This is just to give you an overview. This is like a battery pack, consists of 3 states, like cell level, where electrodes to tap to have the case sealing we have seen, where anode and cathode with electrolyte and different terminals can seal. Then module level, different cells to form the one module, and different modules to form a bigger pack to have desired your voltage and kilowatt requirement. So this is one of the example where these are the prismatic cells you can see in the diagram on left hand side. So these are the battery cells, desire AH. Then they are connected with this different bus bars. These are the copper bus bars. Then there is a supportive structure with passive cooling structure and liquid cooling at the bottom. So bus bars and electrode interface to be measured online prior to the welding. These all are welded by the different techniques. I'm going to explain that. Then cells are placed at a constant distance from each other to ensure the cooling and to prevent overheating of the cells. Then there is a initially cell sorting, depends on the different IR, internal resistance values. When cell manufacturer manufacture the cell, you get the cell, then you can sort, depends on their IR, internal resistance value. Then you can put it in the frame. The frames are stacked. Then you can do the manual welding or something. Then it is semi-automated process. Then you can attach the different cells on the frames, bend the current collectors up to 4 volt. Then these current collectors, then there is a board. Then you can test the cell modules. Then you can insert the cooling device and assemble the cooling device. Then this involve assembly of your battery management system and sensors. Then you can insert these modules on the contact rail and assemble the cell modules. For this process, you can do the different end-of-line testing, which after you can make the battery pack, you can deal with the different charge-discharge process, then you can take the leak test, then IP67 and so on. So this is to just give you an overview. What is there inside the battery pack? The cells and modules, like a cell casing, having the voltage sensor, temperature sensor, self-fusing and bus bar, and bus bar terminals. So you can see it is these are the battery modules, compact, surrounded by these are the cold plates connected with inlet and outlet. And then there is a battery fuse connector pre-charge. And this correspond to a complete battery packs. So in the battery pack, there is a batteries that you can see here with the modules which are connected. Then you can have the disconnect unit with different fuse contactors, pre-charge components, wiring harness, high voltage and low voltage connectors by manual disconnect called MSD. Then bottom up and top up enclosure with sealant so that your battery pack is IP67. So this is just to give you an example. When you select the cell, there is a series parallel configuration. Then you can see the mechanical structure with the given boundary conditions. Then you can do protection control unit, control system. So one of the major challenge in manufacturing is design with the given to the certain dimensions, then supply chain management, then manufacturing flexibility, that in the same line you can't do the cylindrical cell pack assembly as well as prismatic cell assembly. You have to do the changes and you have to control under quality standards. And more important thing in lithium ion batteries is these batteries are very much sensitive for the operating temperature. With the high degrees thing, they are not possible. Then it is important to control, have a thermal behavior. So different softwares can give you the rate of charge discharge, having the ambient temperature range, can predict the thermal issues. But one of the important thing is there are certain, because these are the high volatile material like electrolyte, which is going to decompose at very high temperature, which leads to a capacity fade of your battery pack. Then there is a continuous side reactions going on between anode and cathode and electrolyte because there is ion transfer. So on the surface, there is an impedance which can rise to a power fade. Then decomposition of the binder, these are the material which can give the mechanical instability. Then if your battery can go under the thermal issue, then it can propagate into a thermal propagation. Then lithium plating, which is irreversible loss of the lithium, and capacity fade, as well as the electrolyte will be decomposed, can loss in the electrolyte decomposition at lower temperature. So always your battery pack for the higher kilowatt hour, specifically with the India specific, it can help you. You can have a good cooling system, so you can prevent thermal runaway issue over the period, because during the charge and discharge the heat is generated, and if the outside temperature is higher, you have to control your cell temperature. So there are different ways where you can join the different cells to form the modules, like arc welding, ultrasonic, laser welding, clinching, and screw and bolt. So these are some of the types where cylindrical cells can do by these ways. Where better way with the laser welding, where you have a lower internal resistance after you make the modules. Then same with the prismatic cells are mainly done by the laser welding to have a good optimized performance. Pouch cells can be welded by laser welding way. Even in the laser welding, laser wire bonding is commonly used even by Tesla and other companies. So there is no need for the stamp bus bars. No positioning to rigid the connector is required. It's very flexible design. So from cylindrical cells to various, you can have the higher capacity cells you can do. Then there is always rigidity with the welding of the bus bars. You can check these welds visually. Then the laser spot welding bus bars can be also used, and laser lap joint weld bus bars. I'm not going into the details. I'm just going to show in which way you can do the various ways to do the laser welding for joining the cells and form the modules. But there are very much critical factors which play a role. Like when you do a cell sorting, the pouch cells are vary with the different form factors, with the surface is not stiff. Then it's always difficult to have a cell sorting for the pouch cell. It's a complex, so larger surface area. So there is a bulging or the gas evolution takes place when there is a pouch cell formation, pouch cell form. Then you have to handle it very precisely. No contamination of the surface, low contact pressure, and so on. And stacking and the handling of these cells play a role. Then contacting of the current collectors, which can be lowest possible thermal load during the process, because it can lead to fire hazard. Then production, these are the critical factors that we have to take care in the different steps of the pack making, where when you go to a production, there are different techniques. Like you can see the ultrasonic welding or inspection of the welded joint for the full functionality by the voltage test. Then contacting of the BMS and the sensor systems for the thermal as well as voltage sensors when we put in the BMS and the battery packs. The sensors are very crucial. They can be damageable. So we need a high precision. Then while putting, there is a possibility of short circuit by inaccurate positioning of these sensors and printed circuit boards. So we have to be very high degree of automation is required. Then high precision handling tools can be used. And when we are assembling or inserting the modules, attachment to the module connections, there are the high voltage screws or a chip formation or the short circuit is going to happen. So these flexible cables are a challenge for the automated handling because it's a heavy load is there. Then for that, we can use the sophisticated screwing technology. Every torque has a specific sensors. So with that torque, sensing technique. Only you can do the screwing with the specific screw uh, on a production basis. And end of line testing, there is a high current for the charging and testing of all cells. So there is a high pressure while your leak tightness is involved. It's lead to a burst also while you are tightening the given modules and all. So burst disk required and testing equipment, which can be especially free DC technology, low voltage can increase. So these are the some of the crucial parameters while you are making the packs, including cell sorting, precise handling, contacting of the current collectors, and so on. An end of line test report, if you make any battery packs with all this, so you get an end of line test report, includes the voltage check, IP67, leak test, cold plate, bus bar check, everything in the report. So we can make sure your battery pack is safe and ready to use when you are putting into a vehicle. So with this technology, we have seen on the lithium ion batteries, there are some technologies which might come in the future. There are some challenges in some fundamental challenges, some are manufacturing challenges. So I just wanted to just touch base upon some of the things. The sodium-based batteries, where sodium ion or sodium sulfur batteries use molten sodium sulfur electrodes, which can be separated by ceramic electrolyte. And people are trying to use for these batteries for stationary storage application, having larger cycle life. The cost is very cheap, but energy efficiency is from 70 to 85%. This is one of the technologies, like people are using sodium sulfur or sodium ion batteries. Then vanadium redox flow battery, where vanadium liquid electrolyte consists of dissolved vanadium with the mixture of sulfuric acid and water. Can be have anolyte or catholyte with different oxidation state. The membrane separates two electrolyte and can be have proton conducting. But this redox flow battery need a huge space basically, and having a larger cycle life, but the cost is very high comparatively the other technology. Then solid state battery, it's one of the upcoming area where solid electrolyte consists of inorganic ceramics and polymers. So these are some of the combinations people are using as a inorganic ceramics with sulfides, oxides, phosphates, and solid polymer. There are some advantages with liquid lithium ion batteries over a solid state. One of the advantage in lithium ion battery is low processing costs, flexible separators which can high mechanical stress, then high ionic conductivity only at room temperature. Self-discharge may reduce shelf life, where the solid state battery are still the challenge with the manufacturability. It is having the great thermal stability. The electrolyte use are non-volatile, high energy density, high tolerance. But so these are the things people are trying with the solid state batteries. They are coming up. So it's a 5 to 6 years time down the line where hope we can have cost-effective solid state batteries. Then one more new technology people are trying with the lithium oxygen battery, where lithium metal, then electrolyte separator and gas diffusion electrode, which can be take the oxygen from air, reacts, and it has the energy density close to oil, diesel and petrol energy density because of the oxygen and because of the high transport phenomenon. But in lithium oxygen batteries, there are still fundamental issues with whether it is safe, it don't have larger cycle life. So to give you an example, I just wanted to show you, like there is a lithium anode, then electrolyte and gas diffusion electrode. So during the discharge process, oxygen is coming from the air, can react with then the electron transport happen. Then you can see there is a lithium ions react with the lithium oxygen, react with the catalyst, you can form Li2O2, lithium peroxide. And during the charge process, this lithium oxygen can react with the catalyst and have the transport phenomenon from anode to cathode. You can see oxygen can come out. It looks very simple, but there are a lot of still fundamental issues in terms of the cycle life and many other. I used to make the lithium oxygen batteries earlier with development of catalysts, but there are so many byproducts, so the cycle life is very much limited, though it has great potential. But still, scientists are resolving to resolve the issue. So as we seen, the one of the fundamental thing in the battery development from lead acid battery with 40 watt per kg to nickel manganese hydride lithium ion batteries, now next generation high capacity lithium ion batteries. People are trying with the different alloys to get more energy density, because at the moment we wanted to have higher range in a single charge, where the high energy density people are trying to get with lithium oxygen battery, lithium sulfur or solid state, to see whether they are sustainable and manufacturable in a cost range. So this about the technology and my current organization, we make lithium ion battery packs and BMS. That's a know-how in-house technology, where we have more than 135 different battery pack designs used for the buses, trucks in India and globally. In a single battery pack, we can do 1 to 300 kilowatt hour with 12 to 750 volt. We do a lot of fire tests, safety tests. We can protect our cell level, module level and pack level with the thermal runaway protections. Then we have a co-proprietary on the fusible link and address the single cell failure in the battery pack. We can have the hybrid current collectors with unique vent controls, especially for thermally and electrically insulated barriers. We do active cooling as well as heating at cell level. We design the battery packs with different vibration and strain tolerance. It's have our own BMS with multi-level safety protection, vent detection, and data loggers. So BMS, SW, and HW design are in-house. We are based in Pune, where we have semi-automated assembly line, where up till 250 megawatt hour. We do with the production capacity. We work with ICAT very closely. We have a lot of certification from them. Then we have various products with the BMS as well as with the battery pack for 2-3 wheeler, and develop the system with automated assembly line. So these are some of our packs which are running in India for the commercial segment, buses and trucks, with 660 volt with liquid cooling, NMC. We are cell agnostic company where we work with the different cell suppliers globally. With battery packs are running with liquid cooled over 1 million kilometers in Indian conditions. Thank you. You have any questions, feel free to ask. Thank you. Hello.
Thank you, sir. Thank you for your
Yeah.
knowledgeable session. It will help us all greatly. Now we have two more questions from our audience.
Yeah.
So, question from Mr. Gaurav Heda. Do you see battery replacement station will be key in India market to avoid fast charging?
Yeah. One of the thing is battery swapping. You mean to say for
Sir,
two-wheeler?
yes, sir.
Yeah, for two-wheeler segment, it makes sense. There are some good replacement station. Uh, I can say like for two and three-wheeler, especially for two-wheeler, it can make sense for the battery swapping stations. But replacement station, it's still there is a lot of investment in terms of the robotic arm and all that, and with the weight is concerned, so it's not that feasible. And fast charging, it's good to go, but that will impact your cycle life. Where you want your battery pack to be fast charged, say uh, 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 every alternate day, and you want few years life, which is not possible. You can do fast charging, it will impact your cycle life.
Okay. So next question from Mr. Avinash Kale. Do you discharge all the cells before welding?
Uh, Say, can you repeat?
Sir, do you discharge all the cells before welding?
We do 30%. Cell manufacturer normally send to 30%, and then we do. Then we have a complete cycle. Yeah.
Okay. Next question from Mr. Anupam Agrawal. Why we always combine cells in series and parallel to make a battery pack, and why not instead use a single such large pack?
Yeah, as Dr. Mishra has explained, why people do series parallel combination to achieve, say, in your the kilowatt hour, you want the voltage. Why we are not doing, say, for example, why Tesla is not doing, say, 100 kilowatt with 48 volt? Because if you need a high power, you need a high cabling, and that add on to the cost and many other safety parameters. So that was the reason we do a series parallel combination to achieve certain kilowatt with certain voltage.
So next question from Mr. Balaji B from Chennai. How much is the value addition percentage when you manufacture packs?
Uh, Only the modules or cells. Initially, the modules will come from outside. Rest of the things we have done localized. The BMS, everything is localized, made in India, including the software. That is the brain of the any battery pack, I can call it, and battery acts as a heart. At this moment, nobody is making cells, but it's a matter of few years, then we can have the Atmanirbhar and we can get the cells from India. There is a movement already going on with PLI scheme and government of India. So I can say at this stage, say 30 to 40%, we have localization. Because in battery pack, 70% cost and everything come from the cells, and that we are not making.
So next question from Mr. Avinash Kale. How are the different battery modules connected together to form the pack?
You can have different modules. You can connect it by the different bus bars. These are flexible bus bars. You can connect the modules with different sensors, and every module has your master slave combination with the BMS through CAN communication, and they can connect it.
Okay. I think we have answered all the questions. No, actually, one more question from Mr. Lavkesh Thakral. We should not do fast charge on regular basis or not?
Yeah, you should not do fast charge on the regular basis. That's true.
Okay, sir.
If you do that, you will impact your cycle life. But if you have the requirement, you have to justify that.
The next question from Mr. Raghav Kulkarni. How recess time is to be provided in between charge-discharge cycles in case of cell chemistry is lithium ion.
Normally, cell supplier gives you a certain protocol how the cell should operate, like the limit or boundary conditions, you can say limit. So in that region, you can do your charge discharge, whether it is fast charging or slow charging, he can specify. If it is give 0.5 C, means for you, it will take 2 hours for charge, 2 hours for discharge. If your cell operates at 1 C, so similar way you can do faster. But it is given by the cell supplier because this will involve the warranty of your battery pack, which is very important for your vehicle.
Okay, next question from Mr. Sudhir Kumar. What is the best type of cells for larger pack capacity, prismatic or pouch? And what is the best welding for pouch design system?
It's a good question, but there is no single answer because there are like a spider chart, like there are various parameters like power, energy density, cost, safety, performance. So in that chart, you can check with your application. People, Europe, everyone is using with the NMC high energy capacity materials because they wanted to have a maximum energy in smaller dimensions, because the dimensions are very constrained by the vehicle. If you want to have truck or bus application and you want larger capacity, you use the NMC chemistry. Then for safe or other things, you can use LFP chemistry, where because the energy density, which is a theoretical property, theoretical inherent capacity of that material, it's very specific. So yeah.
So next question from Mr. Firoz Khan. How do we ensure fire safety of battery packs for on-road use purpose?
On road?
On-road use purpose.
Yeah, the one of the thing is it for 2 and 3 wheeler, it is very difficult to use the liquid cooling because it add the cost and complication because there is not enough space to put that. So people use air cooling and select the right cell for their application. And someone earlier mentioned to Dr. Mishra about the phase change material. People are trying. Still, there are issues because in the phase change material, if you are driving your vehicle in Rajasthan, say 45 degrees C, you use phase change material. You gone there and your battery capacity goes down and you need to charge your vehicle. You can't directly put your vehicle because phase change material already expand and it has to cool down. So you need a certain time to wait till you put for the charging. So similarly, for the different applications, you can use the different chemistries and do the cooling mechanism, basically.
The next question from Mr. Amit Goyal. Why it is recommended SOC 80%?
Yeah, it is, as sir also earlier mentioned that, like normally it is from anode to cathode, ion exchange phenomenon. There are always the limiting factor, how much you can put it. And cell supplier gives you this condition, say 80%, your cell performance is better. because of the safety, all the parameters that he done. It's not only he gives you a cell, he do more than 1,000 tests when he develop the cells. So at that different condition, cell supplier, if he got the confidence, it depends on the duty cycle, he can increase from 80 to 90% also DOD to give you more energy density.
Next question from Mr. Rakesh Panda. How to handle battery in cold regions?
Yeah, normally people do the liquid cooling. Similarly, the liquid cooling, we also do the heater, so that we can heat the cells to activate the energy at say -15, -20, and activate the energy basically. To use the heat plates and all that.
Next question from Mr. Shahir Javed. Does every module require to have a BMS separately or only one for a battery pack?
It depends on your BMS capacity. In BMS, how many cells it can monitor, because each and every cell voltage, temperature plays a very important role. So depends on the how good your BMS is. If your BMS can handle 100 cells, which are in a one module, you can use one single module or BMS also.
So another question from Mr. Firoz Khan. Does fire extinguisher required for fire safety for lithium ion batteries?
Yes, there are certain types of fire extinguisher, different class, especially for lithium, for smaller battery packs, especially for when there is a lithium is inside. But normally, normal practice people do, if there is a fire for a big pack and you have accessibility, you can leave that battery pack, because it's not like it's a slowly generating the energy and fire. You can take it with the forklift or put that battery pack in water tank. It will resolve your issue. That's the best practice to follow. If there is a fire of your battery pack, take out the battery pack if possible by forklift and dump in the water tank.
One more question from Mr. Tahir Javed. Can we use bolted type prismatic cell assembly for automotive application?
Yes, you can do that. Yeah.
Another question from Mr. B. Balaji. Government had allowed vehicle manufacturers can sell vehicle-less batteries. Have your company started selling battery packs to end customers directly? What are the key issues involved?
Yeah, we have localized battery pack assembly line in Pune. You are most welcome to visit us, where we get the cells and modules from neighboring country and make the packs, do all the tests in-house from IP67 leak and everything. And we have delivered the battery packs for commercial segment as well as various other small segments also.
From Mr. Raghavendran. Can we combine multiple battery chemistry in packs with robust BMS?
No, people have never. People tried, but they failed because it is more complicated, more cost, and maintaining, because it has to talk with the vehicle control unit, and it has the voltage range, different cooling. So this get more complicated rather than you can have the two different battery packs for the two different vehicles. There is not much gain to use different things. People tried with the hybrid or PHAVs and others, but they are not mixing the two chemistries together. Might be stop and stop for the brakes, regenerative. People use LTO thing and fuel cell. that people can do like a hybrid.
Another question from Mr. Anupam Agarwal. Why don't we use a single large cell? Is it not at all feasible, or research on this being done?
No, it's a manufacturability issue. People are trying now from cell to pack directly with the new technology. They are skipping the module level thing. Tesla, BYD, many other companies are doing that way, where cell can be integrated, different cells, like in a pack. But a single big cell, you can't do it because of the manufacturability, safety, and all that issue. I mean, you can't have the, say, 10 kilowatt hour single cell. You can't.
Another question from Mr. Kamili Raghavendran Babu. Which
Yeah.
is the best joining method for pouch cell terminal tabs?
It's a laser welding. Laser welding. If you do laser welding, you can have the lower internal resistance in your cell, which is one of the key parameter over the period. If you have the high internal resistance, after 1 or 2 years, that internal resistance increase, and that will lead to capacity fading, internal reactions, ACI formation, and so on.
Okay, thank you, sir. Thank you for your
Yeah.
knowledgeable session and all the question answers being answered.
Thank you.
sir. Now, I would like to hand over the session to the Mr. Anup Kakkar, SA and IS coordinator. So please.
Namaskar and thank you and good afternoon to all.
Thank you.
Well, we have had a very interesting session and we thank all of you for supporting this conference, which has been organized by ICAT in association with us under the mentorship of our chairman, Mr. Tyagi, who is Director ICAT, and it has been guided by Madam Pamela Tikku, CBO ICAT, and Madhusudan Joshi, who is the Vice Chair, Seminars and Conferences in SANIS Governing Board. Some of you may know SAE Northern India section is a 20-plus-year-old non-profit technical society, which is member-driven, and it is registered under the Societies Registration Act. We are one of the 4 sections of SAE India affiliated to SAE International USA. Our main vision is to provide a platform for online learning. And this platform is very well demonstrated by the fact that one of our objectives is to bring industry and academia today. And for this conference, we have Dr. Mishra from IIT Kanpur and Dr. Gokhale from the industry. The topic is interesting, and which is shown by the number of questions which have been asked. I have been organizing webinars, conferences. The number of questions that I have heard today being asked of both the speakers, I've never heard so many questions. Clearly shows the interest and the content that has been presented and the inquisitiveness of the participants. Thank you, sir. This is what we need when we organize such conferences and seminars. Now, for financial year 21-22, SAE NIS has envisaged more challenges in the regular event format, and we have taken up new mega events, which we had not done earlier, primarily to reach a larger community and involve more industry, academia, and student members. Some of these initiatives that we have taken are the first virtual autonomous challenge competition for students, which has a unique format of hands-on technology experience, technology display, and knowledge sharing. We expect around 4,000 to 5,000 students attending this virtual conference to start with. It may culminate into a physical event, maybe in 2022. Then we are also organizing the first virtual vehicle handling conference, sometimes in September, October, but looking at the current situation, timelines are all tentative, where people and industry may have an opportunity to demonstrate their technologies in the test track of ICAT. We are also going to do the fourth thermal management conference, which will and a fourth summer school on automotive technologies, which will again this time be in virtual mode, though we wanted it to be physical. Then in December 2021, we are having the ITEC 2021 conference, which is a collaboration with the IEEE of USA. And the theme of this year's conference is e-mobility for Atmanirbhar Bharat. And I'm sure we are in the process of coming out with the invitation and brochures and other things are in the process. Right now, the call for papers is on. And I think the last date given was 30th June, but hopefully it will get extended. Then we have events for, let's say, for school students of class 5, 6, and 7 called AWI. And we have competitions for students like EVSE, Supra, Baha. Then we organize conventions in engineering colleges, enclaves, etc. So these are some of the new events. And in all these endeavors that we do, you all have been a very strong partner and have supported us both by providing experts, various subjects in mobility value chain, volunteers for judging competition, cycle, Supra, AWIM, or giving lectures and sharing your knowledge, students in engineering colleges. But all this that we are doing, we must be giving some benefits to you. So let me highlight some of the benefits that we provide for people who become members of ICAT. One is that you have access to e-magazines, either Automotive Engineering International or Aerospace Engineering magazine from SAE International. You also get subscription to the Mobility Engineering magazine, an SAE India initiative. And you can download all these by clicking on the links that will come to you when you become a member. You also have access to SAE International papers, plus discounted price for SAE Top Tech events. Some of these are free, some of these are paid. Now, with all this, all I can say is that SAE India is an association which is run by you. And so we obviously look to you who are experts in your respective domains to be a part of this platform by becoming SAE members. And let me give you, in conclusion, an example of a very famous athlete, Usain Bolt. You all have heard of him. Well, he won 9 gold medals in 3 Olympics. Total time he ran was for 115 seconds. But the revenue that he earned by running for 115 seconds was $115 million. For 1 second that he ran, he earned $1 million. But to run those 115 seconds, he trained for 20 years. That was the investment he made. My humble submission to all of you will be that if you invest 10,000 rupees plus taxes, makes it 11,800, and get an SAE membership for 10 years, the learnings, the networking, the benefits, the revenue that you will get will be far, far more than what Usain Bolt earned. Because knowledge is priceless. And it has no monetary number attached to it. And more importantly, in these 10 years, you would become a better leader. When I say why a better leader, it's because a leader leverages his relationships. We at SANIS empower you to take initiatives and come up with new innovations, to improve your decision-making skills. We appreciate your efforts. You help in improving your own efficiency at your workplace when you are imparting and giving training or judging people. And most importantly, you are building networking and building relationships. So this is the acronym. You look at all the alphabets of leader, and this is what SAE helps you become in the long run. So I'm sure you all have had a very enriching experience this 2 hours or 2.5 hours of interaction, and we hope that you will continue to be associated with this. Thank you. Thank you so much once again.
Thank you, sir. Thank you.
And by the way, we have a handout which is there on your with the link that has been sent to you, which really provides the membership benefits and an overview of SANIX activities. I would strongly recommend that each one of you download those, go through it at leisure. It has my contact details. Any queries, and if you want to get associated, drop me a mail or a phone call. We will do the rest. Thank you. Over to you.
Thank you, sir. Thank you. Thank you all for joining today for this webinar. And please stay healthy, stay safe. Thank you.
Thank you. Thank you, everyone.
Thank you.
Thank you.
Bye-bye.